Welcome back. Now we're going to explore how we can convert an alcohol to an alkyl chloride. Alkyl chloride down here. And we can't use PCl3. Doesn't work like PBr3 does. One big reason is right here in the previous mechanism. Just make a note, doesn't work. Sad. For the PBr3 reaction here, if we don't have a very good nucleophile, this reaction doesn't happen. And Cl minus does not cut it right here. So if this is Cl minus, the reaction stops here and you don't see anything of the alkyl chloride that you would want. So we need to change it up a little bit. We're going to use this chemical here. It's called thionyl chloride. SOCl2 is called thionyl chloride. And pyridine is this guy here. And its role is quite simple. Proton scavenger that knows how to react with strong acids only. Reacts with strong acids only. Not weak acids like alcohols. Has to be a strong acid like an oxonium, pKa -3. But we don't start with an oxonium, so don't react the pyridine right away. Alcohol is attacking sulfur. Why? Well, the sulfur is very positive. Why? It has 4 bonds to more electronegative atoms. 1, 2, 3, 4. Sulfur 2.5, chlorine 3.0, oxygen 3.5. Why do we not just break off a Cl minus? It would make this mechanism a lot simpler. It would make our lives a lot easier if we could just break off Cl minus like we did with PBr3 right over here. Bust off the Br minus so you can use it right away in the next step. Why does that not happen with SOCl2? Very simple reason. Given a choice of breaking a sigma bond between S and Cl or a pi bond between S and O, pi breaks before sigma because pi is weaker. It's just a general story that's always true. So you broke the pi and you made an O minus. The O minus resonates back and kicks off a leaving group. Hey, what do you call a reaction that's going to make a new pi? There's the new pi right there, new pi. And kicks off a leaving group. We have a name for that. This step is called elimination. I bring it up because in chapter 9, we put words to these things. Let's try to make these words work outside of chapter 9. So we have an elimination step and then followed by an acid-base step. And I'm just going to point out something. Number these steps. Sequence, if you go 1, 3, 2 is acceptable as well. I'm not picky. In fact, you'd have a good argument saying acid-base reactions are generally very fast. It's easy to get to a hydrogen. Maybe 3 should be before 2 because that's an acid-base step, right? And the truth is, I'm going to take either this sequence, 1, 2, then 3, or you could do 1, then neutralize the oxonium here with the pyridine. So just come over here and grab this H, make a neutral O, then do these arrows for elimination in step 3. And then the best part of every lecture is when the teacher contradicts what he said like 2 minutes ago. Cl- is acting like a nucleophile in an SN2 reaction, which is why I said PCl3 doesn't work on the previous page. Cl- is a poor nucleophile. What's going on here? All right, now Cl- would not work on the previous page. We have a situation where there's a carbon with a nice leaving group. It's excellent. It's oxonium. And I have a very strong nucleophile. Makes the SN2 happen. All right. Now I have a situation here. Leaving group doesn't even look like it's an excellent leaving group. That's not the problem, actually. The problem is this arrow doesn't happen at all because this thing's not a strong enough nucleophile. But we overcome that problem because this thing that's leaving, if you look at it carefully, it's making a pi bond between S and O, and another chloride's leaving here, and you're generating this SO2. And the most important thing, you can't underestimate the power of a little letter sometimes. That little letter there, G. That's not an excellent leaving group. I need a superlative above excellent. It's an exceptional leaving group. It doesn't even follow our definitions of leaving groups from before, where the conjugate bases of a strong acid is an excellent leaving group. No, this thing has everything to do with this one word. The reaction is driven by entropy. Anytime you generate gas molecules that weren't there before, it's an entropy reaction. So we can overcome the deficiency of a chloride not being a very good nucleophile by having a leaving group that is exceptional. And there you go. And I'm going to do a version of this where I do switch steps 2 and 3. All right. And here's our chemicals. And pyridine. What color should pyridine be? Green. And what we're going to get, there is a backside attack in this mechanism. So the H gets pushed to the back, replaced by Cl, and we get Cl- next to our pyridinium ion. You heard me right. Pyridinium ion. Where'd that name come from? Well, pyridine's conjugate acid is pyridinium. Right here, pyridinium. And that's anion, cation. And what's the driving force for this reaction? SO2. One of the O's was there from the beginning. The other O's in blue. And I wonder if I'll get everything I need. I think I did. So I'll do a quick rundown of the steps up here and see if we can translate it without having them in front of us down there. Attack sulfur with lone pair on oxygen. That's the words. Pi breaks and becomes O-. And then we're going to do the acid-base step. Pyridine's going to grab the H from this molecule. Then we'll do the elimination step. Just like I said here, 1, 3, 2 is going to work too. See if we can remember all that good stuff. Lone pair on the oxygen. Attacks sulfur, the most positive atom there. Pi breaks, becomes lone pair on O. Draw the result. Got the H still on the O. New bond to S, O minus. Still got the 2 Cl's. Don't forget oxygen with 3 bonds is an oxonium. And that means you can neutralize it. Why? Because it's a strong acid. Pyridine reacts with what kinds of acids? Only strong acids. So as soon as I see the strong acid, I can react to pyridine. How's that? Another reason to prefer this order of steps. And the other, oh, yeah, somebody would have made a comment over here. There's no reason for that nitrogen to have a positive charge. If you go back in the video, I'm pretty sure I said the conjugate acid of pyridine, and I didn't draw the H on it. There's pyridinium. So you just made that. Mechanisms help us catch mistakes. That's good. Sulfur O minus needs a lone pair because one of the lone pairs is going to resonate and kick off our chloride. We need a chloride nucleophile. Poor as it may be, it's going to be good enough for this next step. Oops. Getting ahead of myself. H still on a wedge. I haven't touched that carbon yet. O, single bond to S, double bond to O. Cl minus also. Backside attack on the leaving group. I realize I have a chlorine still on my sulfur. There was 2. I only got rid of 1. What happens to the sigma bond between the carbon and the oxygen? Sigma bond between carbon and oxygen. Between carbon and oxygen becomes double bond between sulfur and oxygen. Sigma bond between carbon and oxygen becomes double bond between sulfur and oxygen. And Cl minus does what Cl minus does, leaves. And that gives the others, all those other products. Oof. We get the SO2 from the right side here. And we get our carbon molecule with the flipped stereocenter. Very nice. I do want to cover the next reaction before break because it's so similar to this reaction. We're going to see sulfur with a double bond to oxygen again. And we're going to see chlorine on the sulfur. But this time the sulfur has 2 double bonds to oxygen. And it's got that short form we've been seeing, TS. TSCl, para-toluene sulfonyl chloride. Toluene. Toluene is methylbenzene. Para-toluene anything is this. A standing for anything, para, toluene, anything. So what's the anything here? It's a sulfonyl chloride. Sulfonyl is S double bond O twice, and chloride is chloride. Is this different than the previous mechanism with the alcohol attacking sulfur and breaking up high bond, making an O minus? No. Is the next step with the elimination this is different than the previous one? No. Is the pyridine doing its acid-base stuff different? No. Can 1,2,3 become 1,3,2? Yes. And the question is, why does this stop here? Because it seems to me in the previous one, we had another step. The halogen that got kicked off, in this step came back and did a backside attack, kicked off the O with a sulfur. What's the reason we could do that? Because this is an exceptional leaving group. The chloride that got kicked off here, right here, there's a chloride, I didn't even show it. There it is. Can't do this. I mean, I'll show it. I don't even want to put it there. Just put a big old, I don't know. I don't feel good about this, even showing that there. Doesn't happen. Burn that into your brain. Why? This carbon it's got an excellent leaving group on it, but it's only excellent. Tosylate is an excellent leaving group. Excellent. What's the short form for leaving group? LG. But it's not exceptional. So we're back to the story where Cl- is not a good enough nucleophile to do this reaction. I'm gonna write that down. Answer. Cl-, not a good enough. No. So after break, we're going to bring this all together because these molecules, the one I sadly have a big X through, is actually a useful molecule. I'll copy it down here. There's its short form. Is a primary RX. That means it's a good molecule by itself. And it's a chapter 9 molecule now. So we could use it for substitution reactions or elimination reactions, depending on what we want to do. And we'll put it all together with what we know so far with the phosphorus and the bromine, the sulfur, and we'll see how this molecule can be made into a molecule that has a new group up here instead of OH. And one of them will be over here will be R, and the other will be the S version of the same molecule. I don't know which side will be R and S. We'll find that out together when we come back, or if you just read this part of the textbook while we're gone. And I'll see you very soon.